So, well, first of all, of course, thank you very much, Max, and also Ethan, Miguel, Irene, for organizing these seminars and for inviting me to present my work here before, as you said, seeing each other in person, hopefully in following conferences. So today I will be talking about the double EFT expansion in quantum gravity, which is mainly based on this paper with Jose Calderón and Alberto Castellano. I will also be mentioning some previous results from this other paper, but mainly the following. So to begin with, let me start by just posing the questions that somehow motivated us to study this, right? So the three big questions that we were asking ourselves were these ones, like what is the structure of gravitational EFTs, how black holes see multi-scale structure that I will introduce in a moment, and whether we can explicitly exploit this multi-scale structure to bound gravitational Wilson coefficients. Now, hopefully by the end of the talk, you will first understand what I mean by these questions a bit better. And also, to some degree, I will try to provide some answers to these questions. Partial answers, but first I will try to define them better, and then I will try to provide some answers. So for that matter, let me start with the first one. What is the structure of gravitational EFTs? And to do that, let me start very simple. So we all know the usual effective field theory for Einstein gravity coupled to matter to some finite number of degrees of freedom. And of course, we have this series, the Einstein-Hilbert action, the matter and the couplings, which includes the spectrum, the masses, the charges, all this, which is something that we very much deal with in the context of the Swampland, right? We usually try to give bounds on several of these things, like the spectrum and how they couple, how the particles couple to each other, and so on. And of course, because we know that Einstein gravity from the bottom up, we know it's a non-normalizable theory, and from our top-down experience from string theory, we know it comes with a tower of higher curvature corrections, which generally, from the usual effective field theory approach, encode the breaking scales of this EFT. So what I'm going to be focusing on for the rest of the talk, and what I mean when I say what is the structure of gravitational EFTs, is actually these two pieces here. And in fact, what I'm going to try to explore today is what is the structure of these higher curvature corrections, in particular, what scales can appear there, what's their meaning, and how they appear there more explicitly. So for the rest of the talk, I will try to give evidence for that. But first, let me just give you our proposal. So the result, just in case you decide to decouple after 3 minutes, at least you get the take-home message. The take-home message is that the structure of this gravitational part of the action basically is captured by this double EFT expansion. So basically, we have a piece of higher curvature operators of dimension n, which is suppressed by some quantum gravity cutoff. I will go back to this. And in addition, we have another piece, which is suppressed by the mass scale of states that were not included in our original EFT. They can be just some particular state or some state which is a part of a tower, which is something we're very used to in the context of the Swampland. And actually, to give a first heuristic motivation for this, let me just think about the two possible kinds of breaking of an EFT that we can think of in this context of quantum gravity. The first one is just the standard, as we said, reaching the scale of a particle of a state that was not included in our original EFT. Now this, as we know from usual UFT courses, right? This can usually be cured by simply integrating in the state. And the key point about this is that this can be done within the language, within the framework of local gravitational effective field theories. In particular, we can integrate in the state if it is some Kaluza-Klein tower or some tower indicating some dual of it. We can also integrate in the full tower. But at the end of the day, the key is that indeed it can be done within the framework of local EFT, maybe in higher dimensions, but in the same space-time dimensions in which the graviton propagates, we can define a new local gravitational EFT. Therefore, we expect this suppression to be the usual one from field theory considerations, namely the scale of the state that we are not including in our theory to the power of n, where n is the dimension of the operator, minus d. Now, the other kind of breaking, which maybe for in the swampland context is even more familiar because it has been the topic of a lot of recent works in the swampland literature, is the quantum gravitational breaking, right? Which basically has to do with reaching genuine quantum gravity effects, and that somehow above this scale, we do not have a local EFT that we can employ. So basically, this cannot be cured by just going to another local EFT coupled, gravitational EFT coupled to a finite number of degrees of freedom. And basically, by just combining these two possible kinds of breaking, we get to this double EFT expansion. So in Planck units, what we can keep in mind is that every higher curvature correction can have these two pieces, like the quantum gravitational one, suppressed by the quantum gravity scale to 1 power n-2. The second one, the field theoretic one, suppressed by some other scale to a different power based by the field theory argument. And the nice thing about this is that, in fact, this double EFT expansion becomes particularly interesting in the so-called asymptotic regime. Namely, when we have that the quantum gravity cutoff is much lower than the Planck scale. Otherwise, I mean, if you think about it, if this were not the case, we could just have something of order n Planck here as the quantum gravity cutoff, and we would just recover the usual field theory cutoff, but for scales n Planck, and therefore no quantum gravitational effects would never be seen, because it's just same power of suppression, but the mass of the other states is generally lower, so we would only access the second part. But precisely because of this hierarchy, and in this regime, this becomes interesting because we can access these two pieces, as we will see. So now, additionally, I would probably, for a general audience, I would need to motivate this so-called asymptotic regime. Probably this is not necessary for a swampland talk, so let me just briefly flash over this. But of course, on the one hand, we have the distance conjecture that motivates the existence of a high number of particles that become light, an infinite number of particles that become light as we approach the boundaries of moduli space, of field space. Therefore, this means that a high number of these guys will become much smaller than the Planck scale. And of course, in this context, we have to keep in mind the emergent string conjecture. And when we go to specific examples, or sorry, to general considerations, we will always keep in mind these two possible kinds of towers, either duals of Cayley-Klein towers or excitation modes of a weakly coupled string. And additionally, there's the species scale, which also motivates the fact that the cutoff associated to quantum gravitational effects also becomes arbitrarily small in Planck units when we approach these boundaries of moduli space, precisely because a high number of states become light, and therefore this species scale that asymptotically we will identify with the quantum gravity scale can be parametrically below the Planck scale. Now, for practical purposes, let me also remind that what the species scale, what this formulation of the species scale plus the emergent string conjecture give us in practice, which is something we'll be using over and over during the talk, is a way to relate the mass scale of a tower to the quantum gravity cutoff that we can parameterize just like this. Imagine if you have some d-dimensional theory with p dimensions decompactifying, this is a good parameterization for the counting of the number of states that appear, and it gives a good parameterization for the quantum gravity cutoff. Similarly, it encodes the emergent string limit when we take p going to infinity. So key message is asymptotic limits. We have asymptotic regime. We have this hierarchy, quantum gravity cutoff much smaller than Planck scale, and then a mass of a tower of states, also much smaller, and up to the order of the quantum gravity cutoff. And then, of course, one more piece of information is that in these asymptotic limits, we know that what the species scale is capturing is what we expect to be the quantum gravity cutoff when we have the top-down construction, namely either the higher dimensional Planck scale, or I should better say the higher dimensional species scale, but at first order this is correct, or the string scale. So, okay, basically I motivated now, like I give some motivation and I gave you the main result of the paper if you want, which is this double EFT expansion, and I motivated why this is particularly interesting in this asymptotic regime. Now, what I'm going to do is in sections 2 and 3, I am going to explore graviton amplitudes and how they relate to higher curvature corrections, to try to understand a bit more from top-down constructions and from general arguments this double EFT expansion that they basically just motivated heuristically up to now. Then in section 4, I will switch gears a little bit and I will try to understand this in the context of the effects or some potential puzzle that can arise from this double EFT expansion in the context of black holes and black hole entropies. And finally, in section 5, I will also change gears a little bit, and I will try to explore potential consequences from this double EFT expansion for Wilson coefficients, gravitational Wilson coefficients, and try to compare with results from the S matrix bootstrap. So let me start with the first part. So, okay, as we said before, there's some intuitive intuition of the species scale, this quantum gravity cutoff in the asymptotic limits. This was the original, in these asymptotic regions, this was the original motivation from Joali and so on. But as we said, we want to study this in the context of higher curvature corrections in gravitational EFTs. Now, this was done like in a more systematic setup, really like pushed for the first time in this work here, where it was studied in 4D n equals 2 compactifications. And the main reason for this was basically that this first non-vanishing correction, R squared to the gravitational EFT, this limit can be computed exactly because it's protected by supersymmetry. And the nice thing is that this gives us a globally defined function here in front of R squared, from which we can recover the asymptotic behavior of the species scale. And this was explored here. But also we can try to define it in the interior of moduli space. Now, for the purpose of this talk, as I said, I'm going to focus on the asymptotic regimes. But indeed, again, we're going to explore this kind of protected higher curvature operators. So the next step to check this is, okay, to a systematic study of these asymptotic regimes in which higher curvature corrections can be computed as precisely as possible. And with enough supersymmetry, there's several examples for this. In a very non-trivial way, this first non-vanishing correction, namely R squared in 4D, or for example, R to the 4 in 10D, maximal supergravity, and so on, in the asymptotic limits is capturing the species scale. And what I'm going to do here is to illustrate as a particular, but let's say enlightening example, the case of maximal supergravity in 10 dimensions, so type 2A. The reason why I'm doing this is because this is the minimal setup in which we have emerging string limits and the compactification limits, because we can vary the string coupling in type 2A string theory. And by making it small, we go to an emergent string limit. By making it large, we go to the compactification to 11D in theory. So in the paper, we study other setups and so on, but for basically the main lessons can be already extracted from here. So what I'm going to do is study the 4-point graviton amplitude, because this has been computed. Several contributions to this have been computed exactly. Some of them are protected. The RPP is protected as well. And the key point is that, okay, the structure of this thing is that I have this supergravity piece, which is the one I present here, which corresponds to this +1, and then some other terms. Now, the different terms have different dependence on the Mandelstam variables, on S and T. And then from this dependence on the Mandelstam variables, we can extract to which higher curvature correction they will affect in the effective action. So in particular, this first contribution, the one that could correspond to R to the 4 in the 10D effective action, has been computed exactly in all these papers, and it has this form. I really don't want to enter into many details, but it has this dependence with the string coupling. This in the string frame, this would be the tree level, the one loop contribution. But now let's explore, as I said, the different asymptotic regimes. As I go to weak string coupling, G is going to 0. This term dominates. And then what I see is that from here, if I write this in string units, I get that this is suppressed by the string scale to the 6, which is precisely what I would expect for an operator of dimension 8, 8 minus 2, 6, Therefore, this is the quantum gravity cutoff in this limit. So this operator, as I said, in this limit recovers string scale. In the strong coupling limit, now one can play the same game. Now this term dominates. And once again, one recovers suppression by Planck scale to the sixth, quantum gravity cutoff to the sixth. Now, at this point, given that we're in the asymptotic regime, and we said that there is, in particular, for example, in the compactification limits, there are these two scales, right? The scale of the tower and the quantum gravity cutoff. The natural question that arises is, okay, then how can it be that I'm seeing this suppression from by the quantum gravity cutoff, which is a higher scale? Is it then that somehow the gravitational piece of the action doesn't see the other scale, right? This is something that one could wonder. And indeed, this also happens, as I said, for R squared, for the n equals 2, and for several other first non-vanishing corrections. So what we decided to do was probably the simplest thing you can do, which is, okay, let's see if it persists if we keep looking at other operators. So luckily, as I said, this setup has been studied, and all other contributions to the 4-point gravitational amplitude have been computed, in particular the one that would correspond to D4 R to the 4 and D6 R to the 4 corrections in 10D. So let's first study the following one, D4 R to the 4. It has this form here, this dependence on GS. Again, I probe the weak string coupling limit. I identify some quantum gravity suppression. Okay. Now I probe the decompactification limit, and I don't find a quantum gravity to the minus 10 suppression. Instead, I find the mass of the tower, which in this case is the mass of the D0 brane or the mass of the KK tower associated to the M theory circle, which basically fits this other pattern that I was saying before. I can do the same for D6 R to the 4. It is more complicated, but one term dominates in the weak coupling string limit. Again, I recover quantum gravity, but in the compactification limit, again, I recover this other setup. So now...
Alvaro, sorry, can I ask you a question?
Yes, please.
Yeah. So the operator that you just showed us that doesn't match the lambda quantum gravity suppression, it had like 8 powers of L Planck and 2 powers of MKK. Does that match to a thing, or is it just pure KK?
Yeah, this is basically because all of this, if you look at it, this is basically normalized with respect to the 3-level part, which includes the Planck scale that goes with the Einstein-Hilbert term, let's say. Basically, this is just, this adds up, this L Planck to the 8 and this other piece adds up to this term in the action. So then, as I was saying, so we see this kind of...
Sorry, maybe just to follow up on Miguel's question is, if I included higher loops to compute this FD to the 6 R to the 4th, would I instead get something that's suppressed by quantum gravity scale? By lambda quantum gravity instead of MKK?
So what I'm going to argue now is that indeed, so here we are considering, let's say from the M theory point of view, I'm considering a one loop, and then I'm reducing this thing. From the string theory point of view, in fact, this is not just one loop. This is the 3-level, 1 loop, 2 loops, and 3 loops. So depending on the frame, it's a different thing. But the key point, this is the dominant contribution to this operator. Even if you include in the M theory frame, if you include more loops, or, well, in the string frame, this is known not to receive any further loop corrections. But the key point is that including any other possible corrections, contributions, this can at best give you only subleading corrections to the ones that I am finding here. So what I'm actually going to try to argue is that indeed it's always one of these two guys, like either this one or this one, that gives you the leading contribution to the corresponding Wilson coefficient.
Okay.
And in fact, because we see these different scales and different suppressions, then the question is, okay, if in general I can have both kinds of contributions, the question is actually, okay, assuming both are non-vanishing, which of them is giving the leading correction to a given operator, right? So this is the question at the end of the day. And in fact, what we can do is to basically for a dimension, for an operator of a given dimension, we can study by using, again, now the emergent string conjecture, so in the compactification limits or in emergent string limits, we can study which term would dominate, because what the emergent string conjecture is doing for us is basically relating, the emergent string conjecture plus species scale is basically relating, as we said before, the scale of the tower with the quantum gravity cutoff. So these two things are not independent. I can basically compare them and I can see when one dominates or when the other one dominates. So let me first start with the compactification limits, which from this angle are the ones that were kind of exhibiting the two kinds of suppressions, right? Because it's where the scale of the tower is different than the quantum gravity cutoff, even though for emergent string limits, there's a more subtle interpretation. I will go to it in a bit. So duals of the compactification limits, as I said, parameterize the relation between quantum gravity cutoff and M tower by this, where P indicates the number of dimensions that they compactify. For this 10D example, to 11D, P equals 1, D equals 10. What one finds is that, in fact, from this analysis, what one would expect is the quantum gravity term to give the dominant piece for a Wilson coefficient if this Wilson coefficient is relevant in the decompactified theory. This means that it is UV divergent, and therefore it is the quantum gravity scale. So just comparing the two, this is the leading one. Whereas for n greater than T plus P, than the number of dimensions in the compactified theory, so when the operator is irrelevant in that sense, this term is bigger. So now, what this means is that assuming the two terms to be present for a given operator, then one or the other dominates. Of course, it can be the case that one or the other is absent, and then the subleading one can dominate. But then what we find is that in the compactification limits, notice that this, let's say, if both are present in all coefficients, this means that the quantum gravity cutoff can only dominate for a finite number of them, because for finite P, only up to some dimension, this can dominate. Whereas this can potentially dominate for an infinite number of them. Now, what this means is that we have, I mean, to basically say that there is an infinite number of coefficients that are suppressed by this, we need to argue that this term is present. If we can argue that this term is present, then it will dominate. And in fact, in maximal supergravity, one can argue this. Like, you can basically check that this contribution, the contribution that for an operator of the 2L R to the 4, we have some integer, there is always this contribution, which is suppressed with a field theory like behavior. And basically, this means that when I reach this scale, I need to change my EFT. Now, keep in mind, and this is an important thing to remember, that I'm saying that we are doing this in this maximally supersymmetric setup, and you could tell me, okay, maybe this is something very special in this case. Now, usually, the reason why we think this is not some kind of lamppost effect is because usually what supersymmetry does for us is to cancel a lot of things. And this allows us to compute things in general, right? So here, what we're showing is that this term is present even in the case where with maximal supersymmetry. Therefore, we would expect it to be present, of course, if there is less supersymmetry. Now, if you look at this term, the other thing that you could worry about is, okay, if I make the mass of the tower very small, this term is going to infinity. And naively, it looks like it is dominating the Wilson coefficient, as we said before. But I don't see this term in the higher dimensional theory. So then you could say, okay, maybe there is something wrong here. So because otherwise, should I see this term above? Like if I go to 11dn theory, I don't get this like KK suppressed term. So what is like really to the 11D limit? So what is going on? And now the answer actually comes to checking massive and massless thresholds. And for this, the amplitudes perspective is a bit better. So far, we have basically been studying the 4-point graviton amplitude, and we have been studying the analytic piece of the amplitude. This analytic piece of the amplitude basically means that it can be reproduced by some local operators. This gives contributions to higher dimensional local operators in the EFT. Now, in addition to that, there is an analytic piece in general of the amplitude every time we have massless particles, for example, which has to do with the fact that with the two-derivative action, we can compute loops of massless particles, and the long wavelength modes basically give rise to massless thresholds, these non-analyticities. But usually these are not encoded in the language of Wilsonian EFTs. These are not encoded in higher dimensional operators, but they can just be reproduced by the two derivative pairs of the action by doing the loops. Now, what is happening here is that the analytic piece, as I said, in the d-dimensional EFT captures the quantum gravity piece, as I was saying, and all these contributions that I was arguing here, which correspond to, from the higher dimensional perspective, when we go down, correspond to integrating out all the KK modes, the ones which don't have any Quasil. So basically, the ones which are not massless. That's why these are the massive thresholds. Now, in addition, actually, in the d-dimensional theory already, we also have a d-dimensional massless threshold. It is not some contribution to these local operators in the effective action, but just because, as I said, this can be recovered by just doing loops using the two derivative pieces of the action. Now, what happens as I go to higher dimensions is that this guy here, this massive threshold, which is the one that would naively give me problems if I go up and I just look at this operator in the higher dimension, combines with this one, and both of them give rise to the higher dimensional massless threshold. What this means is that effectively, these contributions to the higher dimensional, higher curvature operators disappear from my action. But in exchange, I get a two derivative action with more degrees of freedom, which of course I get because I know that 11D graviton, for example, propagates more degrees of freedom than the 10D1. And then similarly, this other piece, the quantum gravity piece, now just goes up. And this is actually the one that I found in the higher dimensional theory. So this is the way in which this behavior that this seems problematic when I take the limit m tower goes to 0 as combined with this and would have, in principle, give me the leading contribution to each coefficient, actually doesn't appear in the higher dimensional action simply because it contributes to the higher dimensional massless threshold in the limit. But still, because when I'm below MT, it gives me the leading contribution, I need to modify my EFT at scales of the order of m tower. So now I basically discussed this, the compactification limits. Let me quickly discuss emergent string limits, but actually what happens here, even though it can seem a bit more like mysterious, it's actually much simpler. In weakly coupled emergent strings, we again have some relation between the mass of the tower and the quantum gravity cutoff. We expect them to be the same, M string. And also we have the relation between the dimensional Planck, sorry, the Planck scale, yeah, the dimensional Planck scale and the string scale. And actually what happens is that if you just rewrite this in string units in terms of yes, the quantum gravity term, the one that we're calling the quantum gravity term, corresponds to GS to the minus 2. Therefore, it corresponds to three level in string perturbation theory, which, by the way, is what we were finding from the type 2A point of view in all these amplitudes. And now the field theoretic piece, what we're calling the field theoretic piece, goes like GS to the 0, so it actually corresponds to one loop. So in this case, what actually happens is that every time we have a non-vanishing three-level contribution, it will dominate. Namely, we will, for emergent string limits, we will have that all the coefficients are dominated by the quantum gravity piece, unless the three-level contribution is not present. This is always in the frame in which, again, I'm doing the perturbative string computation. So having seen these two limits, let me now try to go to the general lessons that we get from here and try to recap this part a little bit. So basically, I was trying to argue that we generally have this, we can have these two kinds of suppressions. For the compactification limits, we saw that in these maximally supersymmetric cases, we also explore some others in the paper, but with more detail, like in these maximally supersymmetric cases, this contribution seems to always be there. Therefore, there is an infinite number of higher curvature operators that receive this field theoretic contribution. Therefore, this means that this series, the field theoretic series, the one here, needs to be taken care of because it diverges at scales as we approach MT. Actually, it is an asymptotic series, but I basically cannot take an optimal truncation. And we really need to correct something at the scale of MT. And then what happens is that it basically, as I said, it basically disappears from the effective action, but at the cost of adding some other massless degrees of freedom in the limit in the two derivative action. Now, in emerging string limits, for example, from 3-level amplitude, one can see that also there is always this contribution. Now it's the 3-level, the quantum gravity contribution. But actually, what we also observe in all examples, and it's what kind of gives more power to this double EFT expansion, is that indeed, like the leading term in any asymptotic regime, the leading contribution to these higher curvature operators is always given by one of these two coefficients. There can be subleading terms. If you look at the expressions that I was showing before for D4R to the 4, D6R to the 4, there were also other powers of GS. But the statement is that in all the examples we've seen, either the full Wilson coefficient vanishes, which can happen also because of supersymmetry. This happens for R squared in D. Or if it doesn't vanish, either this quantum gravitational piece or the field theoretic piece give the leading contribution. So the summary is that, as I said, one has this lower dimensional EFT. We reach the scale at which this series is ill-behaved. We need to correct something. We can complete within the framework of effective local gravitational effective field theories. On the other hand, these ones, the ones suppressed by quantum gravity, just get uplifted. And then once we reach the real quantum gravity cutoff, we can no longer use the framework of local gravitational EFTs coupled to a finite number of degrees of freedom. So, okay, this was this first part, trying to argue like which terms dominate and general structure from this amplitudes perspective. Maybe this is a good point to stop and check if there are any questions before I go to the black holes. Okay, I'll take that as a no. Yes.
I have a question. So you have explained how you have like a tower of like corrections from both like the cutoff and the related to the picture that you just saw and the tower. But would you expect also to have like some finite number of corrections coming, for example, from states that are becoming light in the D-dimensional black mass, but maybe heavy in like the species scale? I'm thinking, for example, extended objects like D brains that are in light.
Well, I mean, so the point is for this piece, for the field theoretic piece, let's say, basically this is a convergent contribution, which can be computed in the EFT, and therefore, because the EFT doesn't, let's say, it's by definition, the mass of the tower is below the quantum gravity scale, because otherwise you would not consider it as some potential degree of freedom that you can include within your gravitational EFT. Here, this can be computed there. The only things that contribute are the ones that are below the quantum gravity cutoff. Now, for the quantum gravity contribution, typically, like either you compute it in the EFT and you cut it off, like it is UV sensitive, you cut it off at what you know would you expect to be the cutoff, which is species scale, which is the string scale or the 11D Planck scale or whatever. Now you can of course always check that within full string theory. And of course, sometimes depending on the frame, you can see this as an infinite contribution from, let's say, a contribution from an infinite number of states. Maybe some of them are below the quantum gravity cutoff, some of them are above, and so on. But the point is that at the level of the effective field theory computation and how it matches the full top-down construction, these are the ones that are giving you the leading contribution as far as we know.
Okay, thanks.
This clear? Okay. Any further questions before I go to the black holes? No? Okay. So then, the second question that I asked at the beginning was whether black holes detect this multi-scale structure. And now you know what I mean by multi-scale structure. So to try to approach this question and to try to motivate it, first of all, I'm going to focus again on the compactification limits, basically because this is where we really have a multi-scale structure because the mass of the tower is different from the quantum gravity scale. And here, of course, these two scales have been motivated from black hole physics somehow. On the one hand, we expect these like neutral black holes to be sensitive to this scale of the tower, to this KK scale, via some instability triggered by something like the Gregory-Laflamme instability, which is the scale. On the other hand, we have this motivation for the species scale and all this analysis into derivative gravity and so on about these minimal black holes, which naively are just black holes that probe species scale of horizons which have size of the order of the species scale and whose entropies are given by the number of species. So the natural question that arises in this context is how to reconcile the fact that minimal black holes seem to probe species scale physics with the fact that at scales much below, we have argued that the EFT breaks down. So to answer this question, let me start with a simple example, a 4D black hole, but let me consider a 5D theory with the fifth dimension compactified on a circle. So when I have that the size of the circle is small as compared to the radius of the horizon, this is a perfectly fine EFT black hole. I can do my 4D EFT analysis and so on. Now let me shrink the size of the horizon or equivalently make the size of the circle bigger. There will be a point where basically they are of the same order. If this is a neutral black hole, we would expect the Gregory-Laflamme to make this object decay from there. But still, if I keep doing the circle bigger, I can have two options for the solution. Maybe one can be unstable, but still there can be two possible uplifts. Namely, I have a black hole in 4D that wraps the extra dimension, so I would see it as a 5D black string, or I have a localized black hole, 5-dimensional black hole. As I said, this guy can be unstable and can be sensitive to this scale, but still I can consider the solution because I can assign an entropy to it. And actually, in a moment, we will see another way of forgetting about the potential instability. But now the question is, which of these objects should I study to kind of, like, if I keep doing the horizon small, which of these two should correspond to this minimal black hole that probes species scale? And let me study that one and see if these KK corrections somehow affect it or not, or how does the thing work, right? So the idea is that indeed from these two options, the one that probably that we should study in this context is this one, because if you think of the localized black hole in higher dimensions in 5D, we know that the species scale there is 5D Planck scale. It's if we make the black hole probe horizon sizes of the order of the 5D Planck length, its area in higher D Planck units is order 1. Therefore, its entropy is small. Its entropy cannot grow with the number of species. On the other hand, some like two derivative analysis again suggests that this guy, in which the horizon transverse to the circle is small but still wraps the extra dimensions, is the one that can be sensitive to the number of species. Therefore, for this guy, how can we reconcile the fact that, as we said, the EFT currently breaks down at a lower scale with the fact that we somehow seem to get something that makes sense in the sense of right scaling with number of species? Now, the strategy here is to consider a very well-known and controlled setup again. So 4D, n equals 2, and we're going to consider D0, D2, D4 black holes. The reason to this is that first, these are BPS black holes, so they won't be unstable with respect to the Gregory-Laflamme instability. Second, is that in this case, these are charged black holes, but the charges determine the uplift. And the fact that this is a D0, D2, D4 automatically determines that from these two options, I'm going to stay within this one. Just to basically clarify this, I'm not going to go into any of the details of how this entropy is computed and so on, because this was the topic of the Swampland seminar last week, given by Matteo and Alberto. Matteo was particularly discussing this piece here. So I'm only going to take that result, summarize the logic very, very quickly and take that result and try to solve this puzzle that I was saying before. So the idea is that for this black hole, so I just take type 2A on a Calvi-Yau and I get a black hole from wrapping D0s, D2s, and D4s in the corresponding cycles. At the two derivative level, this is controlled by the propotential, and the attractor mechanism fixes the moduli. Therefore, I can get the area, the entropy, and all that in terms of the charges. QA, well, Q0 is D0 charge, QA are D2 charges, and PA are D4 charges. Now, there's an infinite tower of higher derivative corrections that can be computed exactly because they are BPS protected, which are of the form R squared, the one that we were discussing at the very beginning that was studied in this paper by Damian, Max, and Conron to define the species scale globally. And an infinite tower of corrections like that, so R squared and then R squared times powers of the graviphoton, can be computed exactly. they are controlled by this generalized potential. But the bottom, like let's say the take-home message is that one can do all that and compute the full entropy index for these objects. And now what is happening here is that I have this entropy for this black hole. This piece here includes the classical part plus the one that comes from the higher curvature corrections that are suppressed by the quantum gravity piece that we were saying before. So this yellow part is basically just the area behavior that you could get from the two derivative for the theory. This piece, the green piece, comes from the quantum gravity contribution, and there is this other piece that comes from the what we were calling the field theory contribution. And this one can be expanded on a series in a parameter alpha, which is basically the ratio between the size of the circle and the size of the horizon. Now, the key thing here is that if I am in this part here, and I am at very small values of the circle, then I can see that this piece, what I was basically giving, like the yellow piece before, the classical piece, is the dominant one. So I recovered the derivative analysis. Around alpha order 1, this thing, the series expansion of this thing breaks down, and then I need to resum it. So this is very much what was happening with, like, it's very much what was happening with the field theory series that I was showing before. It explodes, it gives meaningless results, so I need to fix it. So we see that the entropy somehow sees the KK scale. But the point is that when I actually go to very large alpha and I resum the series, include the non-local effects that affect here, this piece actually resumes to 0. So morally, this is very similar to what I was saying. There's the field theory piece that somehow resumes to the, it's not the same, but like morally, like resumes to the threshold. And in this case, it disappears from here. So this really resumes to 0. So what I see is that in this case, first check the EFT breaks down at the scale that we were expecting it to break down, so MKK. But if I had closed my eyes and forgotten about all the field theory contributions, for this particular object, for the one that wraps the extra dimensions, I would have actually gotten the right answer for the entropy, namely the one that I would get from the two derivative analysis and maybe including the quantum gravity suppressed pieces. Now this, so far, only for this particular example, it is, of course, an open question whether this is a more general thing. It's much more difficult to study in other setups, precisely because if we try to study this for neutral black holes, we also need to take into account other contributions to the corrections, the instability of the objects, and so on. But at least gives an idea of how these two facts, the breaking at MKK and the species scale suppressed corrections, can be reconciled for some particular objects to define these so-called minimal black holes that see the species scale. So this is basically the end of the black hole story. Let me also stop here for a second before spending the last 10 minutes in the other part to see if there are any questions. Okay, I guess that's a no. So in the last part, I'm going to switch gears completely. And what I'm going to do is to study this question that I also presented at the beginning of whether we can exploit this multi-field structure to bound gravitational Wilson coefficients. So as I was saying, so now we're going to switch gears, and what we're going to do is let's assume that the double EFT expansion is valid, and actually in this kind of strong form that I said before, so namely, for any non-vanishing Wilson coefficient, either the quantum gravity piece or the field theory piece give the leading result. This is what we observed. We cannot prove this in general. Maybe there is some way to prove it, like or based on the structures of amplitudes. I don't know. For now, let me just assume this and see whether it can lead somewhere in terms of bounding Wilson coefficients. So the kinds of bounds that we can give are basically two. But the idea is to use this double EFT expansion in the way that I said, sometimes supplemented with the emergent string conjecture to get some bounds on gravitational Wilson coefficients. At the same time, we have this whole group of people working on this S-matrix bootstrap, which from completely different methods are trying to address the same questions, which makes this the ideal area for trying to explore connections. Because the nice thing about the S-matrix bootstrap is that even if you don't know any of the details of how they get their bounds, I don't know many of the details of how they get their bounds, but the question they are trying to answer and the results that they are giving are very easy to understand and are easy to interpret. And basically, this is the perfect arena for trying to connect these things. So what we're trying to do is to, again, use this EFT expansion plus emergent string conjecture to bound Wilson coefficients. And we will use the S-matrix bootstrap to inform the EFT expansion. And at the same time, we will see that we can try to use the EFT expansion to provide targets for the S-matrix bootstrap. Now, keep in mind that this is simply a very preliminary exploration, and we are just trying to see if there is some potential here. So I will do this in a schematic way, but at least I think it can convey the main logic behind it. So the first type of bounds, as I was saying, are just absolute bounds in terms of EFT cutoff for Wilson coefficients. As I said, we are going to understand the EFT cutoff as the one at which we need to change our EFT. It doesn't mean that the full EFT framework, local gravitational EFT framework breaks down, but it means that we need to change the EFT. And therefore, we are going to identify it with the mass of a state. And for the purposes of this section, I am going to use M when I am using only double EFT expansion, and I will use MT as M tower when I'm explicitly using the emergent string conjecture. But just if this is confusing, just assume M and MT are always the same. This is what we keep in mind. So the first kind of bounds are just upper bounds in terms of N, as the Wilson coefficients go to infinity, namely in these asymptotic regimes. And this is simply given by the fact that these two terms can be bounded from above by taking the smallest possible mass and the largest possible exponent. Nothing very fancy, but okay, this is the kind of bound, an upper bound in terms of the EFT cutoff. I will go back to the comparison with S-matrix bootstrap bounds later. And then there are also lower bounds, which now depend on the dimension of the operator. For n smaller than d, both terms can be bounded from below by the field theory piece, because basically it's the smallest one. So this is the overall bound that we can give. And for n greater than d, they can be bound by the quantum gravity scale, but to n minus d, which at this level, because as I said, we are only trying to give bounds on the Wilson coefficient in terms of m. And for now, I'm not assuming a relation between m and lambda quantum gravity. I can only translate to one this coefficient being much larger than an order one number. Now, if on top of this, I use the emergent string conjecture, that gives me this relation between the quantum gravity cutoff and the mass of the tower. And again, the absolute bound is given for p equals 1. I can translate this into the same bound, but now for any dimension smaller than d plus 1. And also, I can now relate the quantum gravity piece, this one, in fact, that is the one that dominates in this case, to the n minus 2, to the scale of the tower. And I get stronger bounds by using the emergent string conjecture. For now, just keep in mind that I get upper and lower bounds in terms of the EFT cutoff, and they are stronger when I use the emergent string conjecture. The other kind of bounds that we can give are basically asymptotic relations between different Wilson coefficients. And this is basically because we have two quantities, m and lambda quantum gravity, and an infinite number of Wilson coefficients. Therefore, what we can do is to solve, basically, for this case, in terms of some Wilson coefficients, and then reintroduce these Wilson coefficients, solve for this case, in the other Wilson coefficients, and try to relate them. For simplicity, what I'm going to do here is to just parameterize lambda quantum gravity as m to the gamma, where gamma is in between 0 and 1. This is only the assumption that m is below lambda quantum gravity. Basically, I'm not assuming any particular relation between them. I will do, in particular, when I assume the emergent string conjecture, once again. But up to this point, basically, I'm just saying that m is below lambda quantum. So for this, I will consider explicitly 10D maximal supergravity because it's where the full S-matrix bootstrap program has provided bounds of this kind. So I consider the R to the 4 coefficient, and it has the quantum gravity piece, which I just rewrite in terms of m, and the field theoretic piece. And if I assume that the quantum gravity piece is non-vanishing, then I get that alpha R to the 4 goes like m to the minus 6 gamma. And this is the first instance where we can use the S-matrix bootstrap to inform the EFT expansion, because actually I don't need to assume this. in this paper from these people, they basically found that this coefficient is bounded from below by some order 1 number. And because the field theory part goes to 0, as m goes to 0, this means that this piece here has to be non-vanishing, and therefore I can relate these two things. And now what I will do is, again, I have other coefficient, d4r to the 4, which according to the EFT structure expansion has this structure, and I just introduce alpha, I just substitute m in terms of alpha. And then I can get upper bounds, which depend on gamma, because depending on gamma, if gamma is greater than 1/5, this term dominates, and therefore the gamma dependence disappears. If it's smaller, this term dominates, the field theory term dominates, and then it depends on gamma. And by making use of the emergent string conjecture, I can take the absolute value of all of this, the absolute bound for these two, which comes from the minimum value of gamma. So if I take just the general thing, gamma equals to 0, doesn't allow me to give any bound, but with the emergent string conjecture I can. And I can also give lower bounds. If I assume that the field theory term dominates, I get this bound in terms of gamma, whose absolute bound comes from gamma equal to 1. I get this 1/3. And if I assume that the quantum gravity piece dominates this other term, I get this other one. Again, the important thing here is that we can keep these kind of bounds, that they are stronger when we combine them with the emergent string conjecture, and that actually in this case, this one is precisely the same that it was found from S-matrix bootstrap results. So let me conclude with this section by now trying to do a quick comparison with the S-matrix bootstrap bounds. And basically, I mean, I told you where the S-matrix bootstrap could basically inform the WFT expansion to get more meaningful bounds. Now, what is the comparison? So first thing one needs to do is to translate our bounds to theirs. They usually bound these so-called adimensional Wilson coefficients, in which they are multiplied by the EFT cutoff to this power. This means at the end of the day that whereas we were bounding in the other language, whereas we were bounding in Planck units the coefficients where they go to infinity, now we are bounding them when they go to 0. But this is just a rescaling. Because m goes to 0, basically this means that now the coefficients go to 0 in the asymptotic regime. Now, for the absolute bounds, there's a ton of absolute bounds in terms of EFT cutoff from this community. But the key point here, I mean, there's a lot of casuistics. One can go check one by one. I won't do that. We don't have time, and I don't want to bore you more with this. But the key message is that indeed they are compatible if we identify the cutoff with the scale of the tower, with m, well, the scale of the first state that we are not identifying. So if we try to identify directly with lambda quantum gravity, these bounds would not be compatible unless the two scales are the same, which of course makes it compatible again. If I have a KK tower, for example, I can apply these bounds directly to a lower dimensional EFT, identifying the cutoff as the mass of the tower. And then if I want, I can complete to my higher dimensional theory, and I can pre-apply them in terms of the quantum gravity cutoff if there is no further decompactifications and so on. But the key point is that from this point of view, we also see this breaking at the scale of it. Second, rescaling relations among Wilson coefficients. Okay, we can just do the same game. We can parameterize these coefficients now in terms of the mass. Same game as I played before. I just rescale them, and then I can try to bound. I basically relate r to the 4 with the mass, and then I try to bound d4 r to the 4. Similar upper bounds. Now the difference is that now, even without assuming the emergent string conjecture, I can get some bound, because now in the gamma going to 0 limit, I still get some absolute upper bound here. And with the emergent string conjecture, I can make it stronger, because this comes from the lower bound and on gamma. And then the lower bounds that I get, assuming the field theory or the quantum gravity, again, no constraint here for gamma equals to 1. This one is again the same as was obtained by the S-matrix bootstrap. So we see how we can recover and find compatible stuff with S-matrix bootstrap. And finally, we say that this one is actually stronger than the one they get. The S-matrix bootstrap people, they get this bound with coefficient 1 here. So having a higher coefficient, since this goes to 0, gives a stronger bound. So even without assuming the emergent string conjecture, we get a stronger bound, and assuming it, we get a stronger bound. This could be a target for S-matrix bootstrap people. And maybe if they find something like this or something like this, we could find indirect evidence from their point of view for the emergent string conjecture. So, okay, let me summarize now. I got to the end. Let me go back to the 3 questions. As I said, I hope by now it's a bit more clear what I meant by these questions, and we have a bit of a clearer picture of how the answers, where the answers could go. The first one was the structure of the gravitational EFTs, and as I said many times, we propose this double EFT expansion. The idea being that when I have a tower of states, I need to, of course, complete my EFT. I can do this within the framework of effective gravitational and local effective field theories. If this is a dual of a decompactification limit, we're just integrating in the tower. This means that this piece of the action, even though it can be leading at low energies, then when I go to the full decompactified theory, then this disappears, goes into the massless, extra massless degrees of freedom, whereas this one stays there. The nice thing about this is that even if I have a low scale, a low cutoff scale, still, because some curvature corrections are suppressed by the quantum gravity scale, I could hope to access this quantum gravity scale, even though there can be much lower scale. So this, for phenomenology, this could be very interesting if we manage to measure this first coefficient at sufficiently low energies, because it could still give us information about the quantum gravity scale, and this is not incompatible with the EFT breaking at the scale of the tower. Second question is whether these black holes see this multi-scale structure or not. What we saw is that the original EFT indeed needs to be corrected at this scale of the tower, but certain black holes and some configurations can probe the species scale physics. But we have to be careful about what we call minimal black hole or how we define these configurations. And finally, what I try to tell you is that by assuming this double EFT expansion, we can find a nice interplay by combining it with the emergent string conjecture with S-matrix bootstrap bounds for gravitational Wilson coefficients, and it will be an interesting arena to explore. So as some possible open questions, we indeed need to study these subleading terms and this multi-scale structure, try to find more evidence either from the bottom-up amplitudes perspective for this idea that for every non-vanishing Wilson coefficient, either the quantum gravity or the field theoretic piece give the leading contribution. Then we can try to generalize this to this black hole story, to more general minimal black hole setups. And as I said, explore more connections with the S-matrix bootstrap. But for now, I will leave it here. So thank you very much.